Now that we have the machinery of vectors, vector multiplication, scaling a vector, and summing vectors, we have the machinery to formulate the problem of solving simultaneous linear equations within a linear algebraic framework. We're not quite there to solve them, but we can at least formulate, and then in the last part of this lecture, we'll actually show you how to solve it. We just need a little bit more machinery to do that. But let's start with the formulation. That's always the hardest part of any mathematical problem. So let me remind you again, we're back to the same system of linear equations. 2x minus y is equal to 1, x plus y is equal to 5. We have seen the algebraic solution. Isolate this for x, substitute into here, back, solve it for y, back substitute the value of y to get the value of x. We have seen the geometric solution, which says that this is an equation of a line, this is an equation of a line, and if there is a solution, then it is at the intersection of those two lines. And now we're going to see the linear algebraic, which is what we will carry on for the rest of this course. And hopefully you'll see that it's a very powerful formulation. It's not just for fun that we are doing that. So let me rewrite this equation a little bit to make the scalar multiplications all explicit. So I had 2x minus y is equal to 1, x plus y is equal to 5. I just want to make explicit that I'm multiplying these by 1, and you'll see in a minute why I'm doing that. Okay, so same system of linear equations, nothing has changed. So let's look at these values over here. So we have thought about this in terms of the rows here, if you will. This is one constraint. This is one equation, one geometric constraint. This is another equation. This is another geometric constraint. Let me think about these a little bit differently. So look at this. This is the unknown x, and notice that it multiplies in this equation 2, and in this equation it multiplies 1. This is the unknown y, and in this equation it multiplies the unknown the value 1, and here the value 1. And then of course on the right I've got this value here. So why did I draw it that way? Because, well, that looks a lot like a column vector. So I've got a column vector 2, 1, a column vector minus 1, 1, and another column vector 1, 5. And what am I doing there? I'm multiplying this vector by x because both components are being multiplied by x. This vector by y, both components are being multiplied by y. So I can take this system of linear equations and I can think about it or formulate it a little bit differently. Can we agree that these two linear equations are the same as this system of linear equations, linear constraints? So what did I do here? Again, I took the 2, 1, that is a single vector, there it is right there, and I'm multiplying each of the components here by x. I'm going to add that to the vector minus 1. I bring the minus 1 in so I can do addition here, and 1 multiplied by y, and that's equal to 1, 5. So let's convince ourselves that these are the same. Well, let's see. So this component is that component right there. This component is that component, and that component is that component. Okay, so that makes sense. But let's make sure we can see the constraint. So first of all, remember that x, a scalar value times a vector, is just x times each of the components. Vector addition is just sum up whatever's there. So this value right here is 2x. This value is minus y. 2x, and then if I sum them up, it's 2x minus y is equal to 1. 2x minus y is equal to 1. Good. So, and then this same thing. This is x, this is y right here, and this is 5. So x plus y is equal to 5. X plus y is equal to 5. So this vector formulation is exactly the same thing, except I've just sort of sliced and diced the knowns and unknowns a little bit differently. Instead of treating this equation as one entity, I've taken the unknowns and I've found what is in common with them, the vector 2, 1, the vector minus 1, 1, and then of course I have a vector over here. Okay. So let's see what this picture is. What does this correspond to here? So by the way, I don't know how to solve this yet. We'll get back to that in a little bit. So here again is my newly formulated system of linear equations. This is one equation here, 2x minus y is equal to 1. This is another equation down here, x plus y is equal to 5. So let's just think about what we're trying to do here. So I've got one vector 2, 1, there it is right there. I have another vector minus 1, 1. And I have another vector, a third vector here, 1, 5. That's this guy right here. And what am I asking for now? I'm not asking for a value of x and y that simultaneously satisfies this equation and this equation. I'm asking for a slightly different problem. I'm asking for the scalar value y such that when I scale this vector by that amount and then add it to a scaled version of this vector by an unknown value y, it sums to that vector. So I'm asking, how much do I scale these two vectors such that when I do the head-to-tail construction, I get that vector 1, 5. It's a slightly different way of formulating the problem. Okay, so I need to be able to scale the 2, 1 along this line here, and scale the vector minus 1, 1 along this line here by x and y, so I get that sum. How do I do that? Well, I don't quite know yet, right? And so, but let's just verify that the answer that we do know is correct. So if you remember, the x equals 2 and y equals to 3 satisfies this equation. We can convince ourselves of that. 2 times 2 is 4, 3 times minus 1 is minus 3, 4 minus 3 is equal to 1. 2 times 1 is 2, 3 times 1 is 2, the sum of that is 5. So 2, 3 satisfies this equation. We don't know how to get to that just yet without using one of the previous solutions, but we'll do that in a little bit. But if that's the case, well then if I scale 2, 1, if I scale the vector 2, 1 out by 2, I get out to here. If I scale the vector minus 1, 1 by 3, I get out to here. And if I sum them, I get the vector 1, 5. So 2, 3 does satisfy this system of vector addition. It tells me how much do I scale these two vectors to get to this vector right here. Again, we haven't figured out how to solve for 2 or 3 yet, the unknowns. But again, well, of course, we'll do that in a little bit. Okay. Now, so that's the big question, is how do we do that? Okay. Again, it's coming. So let's just do a little exercise. I want to make sure that you are comfortable with this vector addition and scalar multiplication. So after I formulate this, please take a second, get out a piece of paper and pencil, and do this little exercise. Show that x equals to 3, y equals to 3 satisfies this linear system of equations. So notice this is the same thing. I have two linear equations. 6x plus 2y is equal to 24. 3x minus 2y is equal to 3. I have formulated this as a vector summation. I'm going to scale these two vectors by some amount such that when I sum them together, I get that vector right there. It's not at all obvious, by the way, why this is a win right now, but you'll see in the next segment of this lecture why it is. But for now, please do the vector multiplication and summation and convince yourself that 3, 3 satisfies this. Just take you just a few minutes to do and just make sure you're comfortable with the algebra here. All right, so let's convince ourselves that this is the answer. So if I multiply 3 times this vector and 3 times this vector, do I get 24, 3? Well, 3 times this is 18, 9. 3 times this is 6 minus 6. 18, 9, 6 minus 6. The summation, of course, is just 18 plus 6 is 24. 9 minus 6 is 3. Now again, so clearly 3, 3 is what I want. It is the scalar values that scale these vectors such that their scaled sum is equal to that vector there. How did I get that? I just gave it to you. Now we need to figure out how to get that solution. And now you're going to see the real power of the linear algebraic framework, is that we're going to frame the solving of linear equations using this vector summation framework. And then you're going to see that the solution comes out very, very nicely, as do many things after that. All right, we'll pick it up in a few minutes.